Log on, tune in, find out. Another good idea from Cambridge.
My work is on studying special solutions of q-Painleve equation, particularly qp2 and qp3, through its Lax pair or iso-monodromy deformation problem. So as a motivation, I've closely followed the work done by Flashka and Newell in 1980 on P2 and P3. So I'll use the method on P2, second Painleve equation, as a motivation and show you how the method works for the continuous case. Then I'll show you how it works out in the discrete case. So a bit introduction about Painleve equations. They are defined to have the Painleve property. They are second-order nonlinear differential equations, and they're said to be integrable. So they have some nice properties, such as they possess the Lax pair or the associated linear problem, which can be derived from iso-monodromy deformation or similarity reduction from the Lax pair of integrable PDEs, such as MKdV, which reduce to P2, and its Lax pair for the MKdV reduced to the Lax pair for P2. Also, I think Sine-Gordon, which is another integrable nonlinear PDE, reduced to the third Painleve equation, and its Lax pair reduced to the Lax pair for the third Painleve equation. So that's where the Lax pair or the associated linear problem comes from for Painleve equations. They are said to be transcendental. That is, the general solution cannot be written in terms of previously non-classical special functions. So they are seen as new special functions, or new nonlinear special functions. But these equations have parameters in them, and for special values of the parameter equations meets special solutions, which can be expressed in terms of rational or hypergeometric type special functions. They also have what is called the Backlund transformation. So the Backlund transformation will take a solution of a Painleve equation to a Painleve equation with particular parameter to another solution to the Painleve equation with a different parameter. So starting from a solution, we can use Backlund transformation to produce a hierarchy of special solutions of the same type with different parameters. Yes. So in their 1980 paper, Flashka and Newell showed that by looking at its associated linear problem, in particular, I'll show in the case for P2, that you can derive special solutions and hierarchy of special solution from the associated linear problem. Also, this hierarchy of special solutions can be written in the form of a determinant, and I'll show that by looking at the associated linear problem, this determinant form can be derived. So this is the spectral half of the Lax pair. Spectral variable is x, and So this is A flat. This is C flat. This is the Lux pair for the second Painleve equation, and it comes out as the compatibility of this system. Compatibility meaning if you differentiate T with to that, and it should equal to if you differentiate this with respect to x. So this gives so this imposes conditions on its coefficients, which are in terms of f, and f is a function of t, which is the Painleve variable, and this gives the second Painleve equation. So this is P2. And it has one parameter, A, which appears in the linear problem as the coefficient of 1 over x. So in this method, we choose to concentrate on this linear system that we analyze mainly this system with respect to x. The reason we do that is that, as you can see, if we this differential system is differentiated with respect to t, it's linear, but the coefficients are function of t, or transcendental function of t. So it's easier if we do linear analysis with respect to x, where the variable comes in only in simple powers. So we can perform linear analysis with respect to x. So when we have a linear system like that, the first thing we look is where the singularities of this linear differential equation are. It's at x equals to 0 and x equals to infinity. It's a regular singularity at x equals to 0 and irregular singular point at x equals to infinity. So from that, we know what kind of form of expansion we can have around x equals to 0 and infinity, respectively. So the expansion of solution around x equals to 0 takes the form So these are the leading powers of the two linearly independent solutions of this 2 by 2 linear system, where A, B, C, D are actually functions of t, because phi is a function of both x and t, really. But we are expanding around x equals to 0 first. And if we substitute this into the equation, we get recurrence relation for A, B, C, D. And what we get is these are the recurrence coefficient for the first vector solution, and for the other one. So as we know from linear analysis that this form of expansion is not valid whenever the leading difference of the leading power are integers. So when, if we substitute in, we found that phi 1, rho 1 is A, so we know that when the difference, which is 2a, are integers, this form might not stand. And from here we can see that a naught and d naught are arbitrary, and c naught, b naught is 0. And this further implies that A even, A odd, and D odd are 0, whereas C even, equals to 0. So, so basically, these four are what we get by just looking at the recurrence relation. And we know that when 2a is an integer, there might be a problem. But let's check the cases. So let's check when 2a is even. We see that when 2a is even, that this form still stands because if we pick the problem point occurs when one more thing I forgot to mention, that we only need to consider a greater than 0 because this function has the symmetry when f goes to minus f, a goes to minus a. So we only need to consider a greater than 0. So the problem point of this expansion can occur at when k is equals to a. So when left-hand side vanishes, the right-hand side, which is a function of its lower recurrence and also function of f, so that might not vanish. So then inconsistency might occur, then that form is not valid. But if when 2a is even, when k is 2a, which is even, we see that when left-hand side goes to 0, so k is even, d will be odd, but d odd is always 0. B, k minus is still be even when k is even, so that's 0, and so d odd is 0. So there's no problem. So the case when 2a is even is okay. So this form we can still use. The next case is when 2a is odd. let's look at the example. So the simplest one, 2a is 1. This says that b1, so 0 times b1 equals to something. If we want this function to be consistent, then we choose I. That since d naught is not 0, then this has to go to 0 if we want no inconsistency to occur. So this, but f is p2, and it says that p2 for this case satisfy a Riccati equation, which can always be linearized by this substitution. So if we substitute this in here, and which is so what happens? So this and this cancel. Says that u is equals to minus t on 2u. So f is equals to, which is an array function. So it says f can be linear, expressed in terms of array special functions. Okay. So this is just simply by asking that this expansion of this form stands for odd integers when 2a is odd. And this also gives us the condition, so where 2a is equals to 1, so a is equals to a half. Okay, so we considered when 2a is even, 2a is odd. And one special case is when 2a is 0. So a is 0. From P2, we can see that for a equals to 0, f equals to 0 is the solution. So let's substitute this into its linear problem. We see that it becomes so this we can solve because this 2x2 system, if we rewrite it like this, we just need to solve that u x equals to minus 4x squared on t u. So we have log u is equals to And similarly, that V is equals to, it's okay. So for the case where A is 0, the associated linear problem can be solved in closed form by simple exponential functions. And happens that these two behavior are the dominant behavior for the expansion of phi at x equals to infinity. So let me do phi expansion at x equals to infinity. We know that it's an irregular singular point, so its expansion has this form. And if I substitute this into the first linear system, I get conditions on what these are. And to leading order phi at x equals to infinity is 1 minus. So we get that gamma naught is 0. Theta 1. Let me call theta equals to so I don't have to write it all the time.
There is no logarithm term?
Sorry?
There is no logarithm term?
The
Just
logarithm?
x in some parallel.
No, for this particular linear problem, there is no logarithm term. It can be checked where alpha 1 is differentiated with respect to t. Gamma 1 is I f 2. Theta 1 is So we see that the coefficients of expansion around infinity relates to P2 in such form. I also need to do this. So I found the recurrence relation of the coefficients for the expansion around 0, but I haven't found out what kind of function they are with respect to t, which is also important in finding special solutions for P2. So if I simply just substitute that into this equation and equate the leading coefficient, leading power, so if I had, So I pick the one with leading power x to the a. And differentiated with respect to t, which only acts on here, which is equals to minus f x. So we're looking at this around x equals to 0, then yes. Here, that expansion was performed at x equals to 0, which to the leading power, I need to equate this one. And so first, to get that, I had to transform this by phi equals to diagonalize this to get the leading power. So yes, so phi actually has a 1, 1, 1 minus 1. And this also will transform b, which so phi naught t would be f minus I minus I phi naught. So we see that to leading order A naught differentiate with respect to t is equals to f A naught, and d naught t is equal to minus f d naught.
You use A and C, so those are C.
That's right. This is from the other one, so so I haven't done this. Yeah, so this doesn't matter. But here we see that f, which is p2, is related by the logarithm derivative of the coefficient of the leading behavior for x to the a at 0. Okay. So we see how linear problem is related, the associated linear problem is related to P2 in such way. So now we have the expansion at 0 at infinity. We look at the few special cases. We see that for when A is 0, the linear problem can be solved exactly. And for when A is equals to a half, it can be solved, the linear problem, for the linear problem to take on this form, it tells us P2 has to satisfy Riccati, which can be linearized in terms of Airy. So the next step is to use the linear problem to find hierarchies of such special solutions, to generalize them. And to do that, so first we'll look at the rational one, which A equals to 0 and F equals to 0. So P2 equals to 0 is the simplest of this hierarchy. So let's look at 2A, which is even. Let's call it, so take A to be an integer. So now that we know the expansion around 0, at 0, I'll put 0 here. Has the form just one more time. So the two linearly independent solutions around 0 are these. And the expansion at infinity looks so in general, this expansion has infinitely many terms. But for the special case when where A is n, we see that the expansion at 0 has leading behavior x to the minus n, and since these two solutions and this solution are the solution to the same equation, so this has to be a linear combination of these two. Therefore, the asymptotic leading behavior should agree at same point. So as x tends to 0, the leading behavior of this solution is x to the minus n, which means this should have the same leading behavior. Therefore, this series summation should truncate at n. So once we decided this, we can use this information to find f. So since this is the linear combination of these two, I can have a set of equations. I forgot to put that, so phi at 0 is 1, 1, 1 minus 1. Phi naught 1, phi naught 2. Okay. So on the left-hand side, we have this to the. So if we say that phi 1 is equals to a linear combination of which, if I write it out, it would be a naught is x to the minus n plus c1 So two leading orders, biggest power at 0. So now we're looking at x around x equals to 0. This we have alpha and gamma n. To look at this at 0, I need to expand e to the theta.
Are the exponent is correct?
The exponent, they are not. Okay. We can't do this because theta is this, so I can expand this exponential function around 0, and LJs would be polynomials in terms of t. Okay. So to this we have L naught, which is equals to B D naught 1 minus. So because of this, if we let a new variable, what is this called again? Xi. The alpha n plus gamma n, then this equation says z n L naught is equals to 0. So let's look at the next order. We'll have alpha n gamma n L1 plus alpha n gamma n minus 1, and L naught equals to B C1 we let variable eta and be alpha and minus gamma n, then this equation implies we have instead eta n L1 plus eta n minus 1 L naught equals to 0. Okay. If I just do 2 more, the one for n minus 2 on the left, I have, because I can see that the next one will be 1 minus 1, so which means I need eta. So eta and L2 plus eta n minus 1 L1 plus eta n minus 2 L0 equals to 0. And 3. So on. So I get 2 n by n matrix equations.
That's a two crown sheets.
Probably I'm not thinking anymore. 1.
I mean, the last formula, is 2L3.
Yes. 1 and 0. Okay. So we see that we can group the equations for z into n by n. I use a different notation to the notes to work it out. 0. So the next one is 2, 1, 0. So these are zeros until they become So the last line comes from the equation of this, and the second one is x n minus 2. If you can see, so it has this pattern. And the other one for eta.
Change notation.
I have I. L. Okay. The read.
And in the right form as well?
Yes. Okay. The reason we want these two set of matrix equation is have a look at what we have here. So we have that.
Excuse me.
Yeah.
I can't understand the right-hand side of the first equation.
This one, like why they're not all zeros.
L of n minus 2, is it correct? Or minus L1, minus L3,
minus 2. Okay. It depends on what n is even or odd. So it changes by 2. So in this case, n is odd. So it goes up by 2. And what case is this? In this case, I did equals to u. So the reason I have this is because these z and eta are related to f, because we get that we know that z is equals to alpha 1 plus gamma 1, and eta 1 is equals to alpha 1 minus gamma 1. But alpha 1 differential with respect to t is equals to I f squared 2, whereas gamma 1 is equals to I f 2. So you see, if we can find gamma 1 from this, then we get f. So how do we find gamma 1? So we need to find these two first. And to get z1, C1 is equal to C1 using the Kramer's rule. C1 is equals to the first row replaced by the right-hand side over the determinant. So the determinant of first row is n minus 2. Etc. And then Ln.
The denominator is slightly wrong. I think you meant the determinant of the first equation. So it should be ln minus 1
Yes.
in the top left.
Yeah, I was looking at the wrong thing. Yeah. And the other one is similar. Okay. So how can we simplify this a bit? So we know what ln satisfy, which I rubbed out. So we know that e to the theta, where theta is equals to Lj. What is my verb? H? J. J equals to 0. So the equation this satisfy gives us a relation for these polynomials in T. So if we differentiate e theta by T, we get Ix e theta. This implies from this definition that Lj T is equals to I Lj minus 1. And differentiate. Oh, that's all I need. It's okay. Okay. So I see that N2 is related to n minus 2 is related to Ln minus 1. So So what I had was eta 1 is equals to so we had minus L and minus 2 is equals to minus, what was the relation? So minus will be I dot T. Will be I and minus 1 differentiated 1. Okay. So then actually I have, let me just call this matrix by its column. So I have this with C1, C2, Cn, and this one is C2, Cn, I, C1 differentiated. But the determinant, the derivative of the determinant is equals to the sum of the sum of the determinant, which each column is letter J. J 1 to n. Okay, so this. Okay, but you see that when see what. But for our particular matrix, that now I'm a bit confused. So this differential. Okay. So column Cn differentiated, whereas the rest of remains the same. But this, because of this relation, that this will be a multiple of the next one. So when two row is the same, it's 0. So for our particular matrix, that this matrix, that the derivative of the whole matrix is just equals to the first one differentiated. Okay, so I can rewrite the numerator as C2 differentiated over this. So which is the derivative of the determinant. The derivative of the log of this determinant. Because this is the matrix different from Z and E, so I call this determinant this. So then I have here log plus. So as you can see, similarly, that eta is equal to dt log minus. Now alpha 1 is equals to 2 alpha 1 is equals to eta 1 plus z 1 plus eta 1. Which is equals to the derivative of log. I think there's a minus somewhere. So it's equal plus all that. Which is equals to, wait, no, I don't want alpha 1 yet. I want gamma 1, because gamma 1 is related to f directly. So to get that, I just, yeah, that's right.
So it's minus on the right. Now it's minus on the right.
Minus.
Get a minus over there.
Okay. What minus?
If you add C1 and eta 1,
Yes.
the gammas disappear, according to your formula on the left.
Okay. So it's, yeah, it's minus. Good. So there isn't a minus here. I have this worked out correctly on paper. So gamma minus I f. Okay. So this is the case when a, which is the parameter in P2, is even integer, and this is P2, so it can be expressed for any even integer. So these are n by n matrices, and this F is the solution to P2 at when A is equals to n. And it's in this nice derivative of log form.
In general, a solution for linear problem has Stokes multipliers.
Yes.
The solutions you are talking about are with zero Stokes.
That's correct.
Because
Yes, these are
psi is
special
of the form
solutions.
exponential times rational.
Yes, and in general there will be log terms as well. But for the case when log doesn't appear and all the Stokes multiplier are zero, the linear problem is the associated linear problem is nicer. So it gives the Painleve equations, which means special rational solution.
We should have a short break.
Yeah, me too. I'm really tired. So I'll talk about this is what Fleshka and Newell did for P2. I'll talk about what I've done for QP2. I found special solutions to P2 for integer values of A in the derivative of a log of a determinant. Yeah, determinant form. Actually, yeah, this Tn was this one, and T minus 1 is this one. So this is in that form where tau n is defined with entries of polynomial. The polynomial are defined by this, and this is the exact solution of when the linear problem is exact solution of the linear problem when A is 0. I gave some examples. So for this, a few values of L. So these are big enough to calculate tau 3 by 3. So you can try if you get really bored in my talk later. So I calculate a few tau using these, and these are the special rational solutions of P2 at these integer values for A. Okay. So I'm going to talk about q-Painleve equations now.
So this is the case that you've lost the log yet?
I have no idea. I haven't checked. I should. Actually, Kajiwara sensei called them, he had something defined, polynomial defined like this, and he called them Devism polynomials.
Say it again.
Devism. Yeah? No, it was in your paper.
Okay.
Ah, that's right. He defined, he defined two determinant representation for these polynomial solutions. One is the Devism representation, and another one is Hankel. So the Hankel one is in yours. This is the Devism one, I think. Okay. So you see that I also want to show, I forgot to show from the last one, that the Backlund transformation. So this is the solution to P2 at A plus 1, which is defined in terms of solution at A and its derivative. So with this, we can generate special solutions of this type by using this. So using this formula, we'll get this. But with the determinant form, we can see that because these polynomials, the numerator and denominator, are special, like what Nomi Sensei said, there's special polynomials. And if you just got numerator and denominator like this, it's hard to get from here back to here, but it's easy to get from here to there. So it's always nice to have the special solution in terms of determinant form. Okay. So now, q-Painleve equations. And q-Painleve equations comes in difference Painleve equations come in two types. One is difference type, where the variable n iterates by integer n plus 1, n plus 2, so on. And the other type is q-difference, which the variable x iterates by multiples of q, so qx, q squared x, so on. And recently there's a lot of interest for difference Painleve equations, and the particular one that I'm looking at are qp2. One of the qp2, the difference between difference Painleve equations and its continuous analog is because we named the difference equations by its continuous limit, and there are a lot of difference equation goes to the same continuous limit. So there are several P2, dp2 and qp2s, and the particular one that I'm looking at is this. So this is where
Maybe you want to use T.
T.
X was the monodromy variable.
Okay. I don't want to use T actually because T is a Painleve variable in the continuous case. I can use Z, and Z does not exactly equals to T. Z goes to T in the continuous limit when Q goes to 1. So I won't use T here, I'll use Z. So this is the particular qp2 I'm looking at. So G goes to P2. This equation goes to P2 in the continuous limit when Q goes to 1. And the reason I'm looking at this qp2 is it comes with associated linear problem. So this form of qp2 is obtained by Mike Hay, another student of Nalini. He found this by performing similarity reduction on q-mkdv. So it's the same as the case for continuous. The P2 was derived from similarity reduction for mkdv and its lax pair. And here we have qp2 and also its q linear problem from the similarity for q-mkdv. Okay, so the lax pair, what else do I want to look at? I want to talk a bit. So, so here, difference Painleve equations have lax pair as well, but not all the, lax pair not for all difference Painleve equations are known, And this particular one is known because the Lax pair come from the Lax pair for MKDV. So he has QP2 and QP3 with the associated linear problem, and there are other q-Painleve equations that has Lax pair, such as the 2x2 iso-monodromy problem for QP6, which was derived by Sakai, and also I think Murata did convalescence on Sakai's QP6 to get the rest cascade of QP5, 4, 3, 2, so on, and their Lax pair from Sakai's one. I found this method only works on 2x2 Lax pairs. So the existing 2x2 Lax pairs are Sakai's one, and this Mike's one for QP2 and QP3. There are Lax pairs 3x3 and 4x4 ones for QP3, or some QP4 something, but I haven't worked out how to do this method on those ones. So works on 2x2 ones. Difference Painleve equations, like its continuous analog, have special solutions. In particular, they have rational special solutions, a hierarchy of them, for special value of parameter. So in this case, alpha would be the parameter for this QP2. There are two types. One is rational hierarchy, and another one is special function hierarchy, which is just like the one we had for P2, as area function has area function as the hierarchy can be expressed in terms of determinant of area function and derivative for P2. The same case happens for QP2, where the solution can be expressed in terms of determinant whose entries are q-area functions, which I'll show here. There are also Backlund transformations for these difference Painleve equations. So I used the method of Nalini. I found a Backlund transformation for this QP2. So it does the same thing as this. Once I have a solution, a seed solution, then I can use the Backlund transformation to generate a sequence of special solutions. But to use the linear problem helped me so I could go from, I have this, but I could have those as well in terms of the determinant forms, because if I just looking at this, I wouldn't be able to tell what the determinant form is. Okay, so now let me do difference linear analysis on the Q-difference Lax pair for QP2. Since it's a lot to write, I'll just write symbols instead this time. So phi. Now, so my two variables are these. This is the spectral variable, and this is the Painleve variable, where a hat implies mu goes to mu on lambda squared, and z goes to lambda. once again, we choose to analyze the linear system with respect to the spectral variable because A is of the form So A is of this form, which is a polynomial in the variable, spectral variable nu, whereas B contains, in this case, the operation is with the Painleve variable Z, and B contains functions of Z. So I'll come to linear analysis without knowing anything about G. So I need to do similarly, I need to do a bit of analysis on this system. We see that we need to, in this case, we can't use the, yes?
You're shifting by eta, not by q.
Lambda.
Lambda.
Find what lambda is in terms of.
Sorry?
1 over lambda, you can think it, oh,
Lambda.
One of the lambda is q.
Oh, okay. Oh. That's obvious to me.
Sorry. So I need to do a bit of Birkhoff theory because we can't use differential analysis on a different Q-different system. So 100 years ago, about Birkhoff developed a theory on linear analysis on both differential difference and Q-difference equations. And he states that for a Q-difference linear system of this form, the A can always be transformed so that A is a polynomial. So A, let me call, so A is, so I'm using a different variable. Okay. So A is a polynomial with, call this n by n. Okay. So A is a matrix of polynomial of degree, highest degree nu, m by n matrix. Okay. And the condition that this has solution is it has two fundamental solution, one at 0. Wait. And the eigenvalue for A naught, let me call them rho 1. There will be m of them, since it's m by m. And the eigenvalue for A mu is sigma 1 to sigma m. Okay, I think that's enough to define. So the two fundamental solution of this system is one at 0 of this form. I forgot to bring my notes. I x to rho I. Okay, it's better this way. And the solution at infinity have this form.
Yeah.
The G's are inside the coefficient, the entries in the coefficient. She hasn't given you the definition of the E's and the N's.
Or the definition is later. No. The first time.
With the variable x. And one more. To solve this linear system, because it can always have expansions, you need to have a connection matrix which connects the two expansions. So this solves the linear problem. Yeah, and here it's chose that way so that this description of phi infinity satisfy this equation with A in this form at looking at x equals to infinity. Ramis has find another function which also does the same thing, but it doesn't have the log in them. Okay, so and also, yes, his condition was the solution to this linear system can have this form if only if the difference between is not equals to q to the n, where n is an integer. So this is similar to the linear differential analysis where the difference of the leading power is not integer. So in the q difference case, this is the condition for these two to exist. So now to look at, I want to give two examples maybe how this works. So the simplest case for this is 1-by-1 case. We'll have y q is equals to 1. Okay. So you see that u in this case is 1 and m is 1. This can be easily seen how to solve. We have we can have a series expansions. I need a new notation which is a q to the n equals to So for this 1-by-1 equation, q difference equation, this is a series solution for this. We can check. I always forget that I can't leave this. So we can check let me rewrite this with y minus yx equals to minus r1. Then this minus that. But qj is equals to 1 minus q, 1 minus qj minus 1, no, j. So this is equal to qj minus j minus 1 xj, which is equal to minus x minus xy. So this shows that with this definition that it satisfies this, sorry. This is the definition for y, no. Oh, excuse me. This is the definition for y, yeah, okay. That's the case for 1 by 1, and now although Birkhoff has the explicit formula for all these three, but it's not trivial once mu is greater than 1. So the only two cases we can solve explicitly are for mu equals to 1. Whereas you can see for our for our linear problem is our mu is 3, so something special has to happen for me to be able to solve this explicitly. So just let me write down the other one. Now this is the 2 by 2 case. So the eigenvalue for A node is A1, A2, and for A1 is B1, B2, and the determinant of A node plus A1 as goes to 0 implies actually is alpha 1, alpha 2. So alpha 1 and alpha 2 are the roots of the determinant of the coefficient matrix. So these data define this 2 by 2 system. And for this one, the solution for this linear system is in terms of phi 1, 2, the Q hypergeometric function, which is defined as such. and where A, B, C are related to A2, Y1, B1, A2, A1, A2, B1, B2, and alpha 1 and alpha 2. And this is done in the work of Lacan, who is a student of Berkhoff. So in this case, it's 2 by 2 of first degree. Is solved exactly, can be solved exactly in terms of Q hypergeometric functions. Now.
So you mean that psi is expressible phi linearly probably?
Yes. Yes. Okay. So now, what do we have here? We have the order is 3, but at least we can expand and see what happens. So if we expand the solution, so we can have formal expansion at 0 and infinity. Let's look at the one at 0. Phi 0. So good. Now this time, if you look at 0, coefficient matrix is diagonal. So it's so we don't need to transform it to get the leading order. So this time the variable is new. Okay. And this form holds, as we've been told by Berkhoff, if only if, when E1 over E2 is not, the quotient is not Q to the integer. And how does E1, E2 relate to our QP2? Here, alpha is equals to E1 on E2. And also, M1, M2 are functions of Z, which depend on F. The dependence is explicit, but I haven't wrote it out.
Is F the same as G that you started out from?
Sorry?
Is F the same as the G that you started out from?
This, which F?
The first line on that board is G.
This,
Yeah.
G, QP2?
But where is the
How
dependence
if
on
one if you are expressed in terms of G?
If you want to know.
Really unflappable.
So E1, E2 is explicit. F1, F2. So actually, you see, F depends on the Painleve variable, not Painleve, q-Painleve itself, but M1. one into functions depending on G like this as well.
E1 and E2 are parameters.
Yes, E1, E2 parameters which related to the parameter in QP2. Okay, so we see that the expansion of the fundamental solution at 0 have this form, but when E1, E2 is that, then this form does not work. But like what we did for P2 in Flash-Gagnon, we look at when this doesn't satisfy this condition, but this form still holds, and this will give special solutions to the associated linear problem. Therefore, special solutions to this QP2. Okay. But before we look at the special parameters, there is one simplest case whenever we have the coefficient matrix whose degree are higher than 1. The simplification, and we can solve the linear system in terms of what is called the Q-gamma functions. And that happens when all the coefficient matrix in A commute, which means A can be diagonalized by a constant matrix. Therefore, this 2 by 2 third degree system is reduced to a 1 by 1 cubic. So, okay, yes. And how do we get that? So this case is when E1, E2 is equals to 1. And for this, we can easily see that the solution to QP2 in this case, which I'll denote as G naught, is equals to minus I Z. So let's see if it works. I hope it does. So it means up is to substitute in this into QP2, we have minus Z squared times the denominator over which should equals to, let's see what alpha equals to. And Z squared G minus I Z squared. Okay. So for Z to the 4, we have minus Z to the 4 because alpha is 1. So Z to the 4, and the other one is I Z3. This one is minus I Z3. Minus I. Yeah, it's minus 2. Yes. So this is the solution for alpha equals to 1. So this we can get simply by looking at QP2. Now we can substitute what G is into the linear problem. So we know explicitly in what these functions are because we know what G is. And it turns out, for this case, the linear problem you see this? The diagonals are the same, so that I don't need to worry. And we can diagonalize, since the ratio of this and that is the same, we can diagonalize A with C. I change back to lambda again, but don't worry about it. So I can diagonalize this. So if I let phi equals to C phi 1, then phi 1 satisfy the other equation also simplifies to these two are my equation for when alpha equals to 1. So it can be solved, as you can see.
It's I1 on the right, the last.
Yes.
What under it?
But it's 30 as well. Maybe, yeah, I'll use this one. So let phi equals to u and v, and u is equals to, just let me call this a1, a2, a3, u. To solve this, I let u equals to where I is equals to 1 minus ai ui, such so that you satisfy this equation. And for each ui, it is solved in this form as a series. Yeah. Okay. Okay. So in the end, u is a product is my variable. And if I multiply it out and then this be minus I. So, because we we can solve the linear problem exactly in terms of Q gamma functions. Should I just give you the result? Okay. So what I found was what I found was I forgot to say that these are functions of the Painleve variable, and from the original Lux pair B, if I substitute this in B, I get that GK is equals to minus I Q 2 A mod K. Okay, so here, because now if I'm looking at when this is integer, specifically n is even, then okay, I can't use scaling. So I denoted the coefficients when the leading power is of integer h minus h. I denoted the coefficient of expansion by h. Okay, so this is the case when E1 over E2 is equals Q to the 2h, an even integer. So then h. So in this case, the solution to QP2 when alpha is equals to Q to the 2h is expressed in terms of the shifts of the leading coefficient A naught, which are functions of z. So this is related to QP2 at integer values of even integer values of alpha, and I found that A naught, the leading coefficient for h, can be expressed as tau functions, tau k, tau h. Tau h minus 1, where tau h z is defined to be of where alpha defined by this. So alpha is the polynomial coefficient in the series expansion of the solution to the linear problem for when we can solve it for alpha equals to 1. So in this way, we found the determinant, the solution at special values in terms of determinants whose entry are defined by the solution of the linear problem at the first spatial value. Okay. Thank you.